Lesson 13.2, Exponential Decay Functions. How is the graph of g of x equals a times b to the x minus h plus k, where 0 is less than b is less than 1, related to the graph of f of x equals b to the x power? Well, the A does a vertical stretch or compress. The H, horizontal translation, left to right. And K does a vertical translation, up or down. Graphing and analyzing f of x equals 1/2 to the x power and f of x equals 1/10 to the x power. Exponential functions with bases between 0 and 1 can be transformed in a manner similar to exponential functions with bases greater than 1. Begin by plotting the parent functions of two of the more commonly used bases, 1/2 and 1/10. To begin, fill in the table in order to find the points along the function f of x equals 1/2 to the x power. You may need to review the rules of the properties of exponents, including negative exponents. So negative 3, that would give you 8. Negative 2 would give you 4. Negative 1 would give you 2. 0 would give you 1. 1 would give you 1/2. 2 would give you 1/4. And 3 would give you 1/8. What does the end behavior of this function appear to be as x increases? Well, as x increases, it appears to approach 0. F of x approaches 0. And I'll show you. Now let's do this graphically. Negative 3 is 8. Okay. Negative 2 is 4. Negative 1 is 2. And 0 is 1. And 1 is 1/2. 1/4. And 1/8. This looks something like this. All right, so I plotted the points on the graph and I drew a smooth curve, and you can see as x approaches positive infinity, f of x approaches 0 from the positive side. All right, now let's complete the table for f of x equals 1/10. So that was negative 1. This would be 100. That would be 10. That would be 1. 1/10. 100th. And then 1/1000th. And try to put the, see, negative 3 I can't put on there. Negative 2 I can't put it. Negative 1 is 10. Put that on there. 0 is 1. 1 is 1/10. And I can't put it on there. It's going to get real close. Quickly. It gets close quickly. Again, as x approaches infinity, f of x approaches 0. Fill in the following table of properties. Okay, so the domain is always going to be x such that negative infinity is less than x is less than infinity, or all real numbers, however you want to say it. The range y is greater than 0, and y is greater than 0 for both. The end behavior as x approaches infinity, f of x approaches 0. The end behavior as x approaches negative infinity, f of x will approach infinity. Y-intercept is always going to be 0, 1, unless it's been transformed. All right. Both of these functions decrease throughout the domain. Okay. Of the two functions, f of x equals 1/10 to the x power decreases faster. Make a conjecture. Look at the table for the property of the functions. What do you notice? Make a conjecture about these properties for exponential functions of the form f of x equals 1 over n to the x power, where n is constant. Well, when you look at that table, let's see here. Notice the domain, range, y-intercept, end behavior, that looks terrible, are the same for both functions. What's different? Well, as n gets larger, it approaches as n gets larger, the function approaches 0 much faster. The steeper, the decline is steeper. You'll also notice that these properties are the same for all of those functions. Graphing combined transformations, f of x equals b to the x power. When graphing transformations, f of x equals b to the x, where 0 is less than b is less than 1, it is helpful to consider the effect of the transformation on two reference points. These two reference points. Okay. As well as the effect on the asymptote y equals 0. The table shows the reference points and the asymptote y equals 0 for f of x equals b to the x power, and the corresponding points for transformed function g of x equals a times b to the x minus h plus k. Now, I would write these down. These are super helpful super helpful for graphing these functions. These for, especially those for finding those points. And then, of course, this is the asymptote. We're kind of already used to that. The graph of the parent exponential function is shown. Use the reference points in the asymptote shown for the parent graph to graph the given transformed function. Then describe the domain and range of the transformed function using set notation. Okay. I'll let you read through A, and when you come back, we'll do B together. So you have g of x equals negative 1 over 10 to the x plus 2 minus 8. So what does that tell you? What does that tell you? Well, A is negative 1, B is 1/10, H is negative 2, and K is 8. All right, find reference points. So you got H, and then that was A plus K. So H is negative 2. Notice negative 2. All right, and then A plus K, negative 1 plus 8, that gives you 7. H minus 1, so that's going to be negative 2 minus 1, which gives you negative 3. And then A is negative 1 divided by B, 1 over 10. So negative 1 divided by 1 over 10, that's going to be negative 10 plus 8 gives you negative 2. All right. Find the asymptote. Okay, the asymptote is K. The asymptote is K. So we have y equals 8. So let's just draw that. Now look back on that other page. What were those points? What were those points? We had negative 2, 7. Negative 2, 7. That'll be right here. And what else did we have? We had negative 3, negative 3, negative 2. So that's going to be that right there. So let's see here. What do we got? And that goes down to there. And it gets right up there next to it. So the domain is going to be negative infinity is less than x is less than infinity. And the range is going to be y such that y is less than 8. Which parameters make the domain and range of g of x differ from those points of the parent function? Write the transformed domain and range for g of x in set notation. None of the parameters affect the domain. So none of the parameters affect the domain. It's always the same. What does A do? A alters the range if less than 0, Okay, if it's negative, what does it do? And let's see, k alters the finite end of the range. So none of the parameters affect the domain. A alters the range if A is less than 0, and K alters the finite end of the range. And when I say that, what I mean is, here's K right here. Okay, if it was 4, it would be down here, and it would. Okay. So let's try this one here. We're going to graph the transform function, then describe the domain and range of the transformation using set notation. Okay, so what is A? A is 3. What is B? 1/3. What is H? -2. What is K? -4. So the asymptote is y equals -4. So let's find -4 here. And we'll draw that. There's our asymptote. So let's see. We have a couple points. That would be 0, 1. They always go through there, and -1, and then 1/b. 1/b. All right. So how these transform? Well, this becomes h, and then h, and then a plus k. Remember that. So that's h is -2, and then a is 3 plus -4. That's going to give you -1. So we've got -2, -1 is right there. All right, that's our first point. And then our other point, this is going to be h minus 1, and it's going to be a divided by b plus k. So h, -2 minus 1, that's going to give us -3. And a, 3 divided by b, so let's see, a over b plus k, that's going to be 3 over 1/3 plus -4. So that's going to be 9 minus 4. I get 5. So -3, 1, 2, 3, 4, 5. That's going to be right there. All right, now let's draw. Let's see here. One of these days I'll learn how to draw a straight line freehand like that, huh? What do we got left? Well, let's see the domain. And that's going to be x such that -infinity is less than x is less than infinity. And the range, and we can see the range, y such that y is greater than -4. All right. And folks, if you're not sure, you can always go on the graphing calculator and graph it and make sure that you drew it right. Writing equations for combined transformations of f of x equals b to the x, where 0 is less than b is less than 1. Given a graph of an exponential function g of x equals a times b to the x minus h power plus k, the reference points in the asymptote can be used to identify the transformation parameters in order to write the function rules. So let's see, write the function represented by this graph and state the domain and range using set notation. So you can follow along in the book, and then when you get back, we'll do B together. All right. Notice we're given a couple reference points here. Those are very helpful. Okay. So we want to find K from the asymptote. And that's pretty easy. Y equals -1. So let's put that. Y equals -1. Or K equals negative. The first reference point was 2 and -1/2. Okay. So So 2 -1/2 equals h, and then a plus k. All right. So h is 2, and then let's see, a plus k equals -1/2, right? Oh, we know what k is. K is -1, so a plus -1 equals -1/2. Add 1 to both sides, so a equals 1/2. Okay, so that's, we'll put -1/2 minus k, and then that's 1/2. All right. The second reference point was at 1, 4. So 1, 4 equals h minus 1, and then a over b plus k. Well, a over b, so a is, we figured a is 1/2, right? So we got 1/2 over b minus 1 equals 4. Add 1 to both sides, so you got 1/2 over b equals 5. And let's see here. So b, and then divide. And I'm getting 1/10. 1/10. And let me show you how I got that. 1/2 over b equals 5. Multiply both sides by b. So I got 1/2 equals 5b. Divide both sides. Divide both sides by 5, and that gives you 1/10 equals b. So that's how I got that. All right, we're not done. So let's put them in. G of x equals 1/2 times 1/10 x minus 2 minus 1. And so y is greater than -1. The domain is all real numbers, and the range is y, such that y is greater than -1. It's not hard at all. Compare the y-intercept and asymptote of the function shown in this table to the function plotted in example 2a. So what can we, let's see. Okay. Notice the y-intercept. The y-intercept, it looks like it has gone from 3 5/8 to 1 5/8. The y-intercept has moved down 2 units, and we could say from, let's see, 3 5/8 approximately to 1 5/8. And what else? The asymptote appears to have moved down 2 units as well. The asymptote appears to have moved down 2 units as well. Okay, and the other one, it was 4, and then look here, 1 and 20. That's getting awful close to 2, so it's moved from 4 to 2. All right. Compare the y-intercept and the asymptote of the function shown in this table to the plotted function in example 2b. All right, let's take a look at this here. The y-intercept is not apparent in a graph, but appears to be greater than -10, while in the table it is 0 right here. Okay. In that, I mean, we didn't calculate it. I mean, you go back and let's see here. Let's see what I'm talking about. Here it is. We don't really, that's not the right one, is it? Example 2b. Yeah. See, we were. Let's go back. You go back up. That's up there at the top. Where's the there? I didn't have a copy of it. See, it's the y-intercept's not apparent. We don't know if it ever even crosses the y-intercept over here. Okay, so we don't know if it ever actually crosses the y. You can't see it in the graph, but here we see it crosses at -0.95. So let's see here. Let's see. The y-intercept is not apparent in the graph. But in the table it's right there. The asymptote appears to be -1 in both. See how it's getting real close to, yeah, so the asymptote appears to be -1 in both. All right, good. Our turn. Write the function represented by this graph and state the domain and range using set notation. Okay, so we're given a couple points here. We're given this point 0, 4, and we're given this point 1, -2. Asymptote's right here. Asymptote is y equals -4. So what does that tell us? That tells us k equals -4, right? So we need to find out what h is, we need to find out what a is, and we need to find out what b is. We need those things. Well, we've got this point 1, 2. This 1, -2. All right. Now, if you remember, that's going to be h h, and a plus k. All right, so this is negative. This is 1. So our h is 1. All right, now we found two of them. And let's see, a plus, this a, we'll leave that. A plus k equals, and it says negative 2. Negative 2. Well, we know k is negative 4, right? So we make that negative 4. So a plus negative 4. Add 4 to both sides, and we got a equals 2. So now we got 2. So, all right, good. And what are we missing? We're missing the b. How do we find the b? Well, we've got this point 0, 4, right? And remember, that's going to be h minus 1, and then a over b plus k. All right, so let's test it. 1 minus 1 is 0. That worked out. So a over b plus k equals, and it says 4. 4. Well, k is negative 4, so we'll put negative 4 there. All right, and then a is 2, so we'll put 2 right here. So 2 over b, and we'll add 4 to both sides. So 2 over b equals 8. And then multiply both sides by b. We got 2 equals 8b. Divide both sides by 8. So 2 over 8 equals b. And 2 over 8 reduces to 1/4. So b is 1/4. All right. Now we can write our equation. G of x equals a times 1 times b, and then that's x minus h minus or plus k plus negative 4. All right. So there's our equation. Not too shabby. Folks, you can always graph it in your calculator and test, and then look for this point and that point there. They'll be there. And you've got the domain. Domain is going to be x such that negative infinity is less than x is less than infinity. And the range is going to be y such that y, and look, it's greater than negative 4. Y is greater than negative 4. All right. And let's try that in our graph. Let's test that in our graphing calculator. So we got 2 open parentheses. Man, look at that. 2 open parentheses, 1 control divide, and it was 4 caret, and then we're going to put x minus 1, x minus 1, and then we got minus 4. I hope this works. It'll be so embarrassing if it doesn't. Control T, and we were looking for 0. Let's see, 0, 4. And then let's look for, what was that other point it gave us? 1, negative 2. Oh, there's both of them right there. Good deal. All right. That worked out good. Worked out real good. Modeling with exponential decay functions. An exponential decay function has the form f of t equals a times 1 minus r to the t power, where a is greater than 0 and r is a constant percent decrease expressed as a decimal for each unit increase in time t. That is, since f of t plus 1 equals 1 minus r times f of t equals f of t minus r times f of t. The value of the function decreases by r times f of t on the interval t plus 1. The base 1 minus r of an exponential decay function is called the decay factor. And the constant percent decrease r in decimal form is called the decay rate. Given the description of the decay terms, write the exponential decay function in the form f of t equals a times 1 minus r to the t power, and graph it with a graphing calculator. So I'll let you read through. Oh, that's a pretty truck. That looks like my old truck. Let you do A, and then when you get back, we'll do B together. So what do we got here? The value of a sports car purchased new for $45,000 decreases by 15% each year. Write an exponential function for the depreciation of the sports car and plot it along with the previous example. After how many years will the two vehicles have the same value if they are purchased at the same time? So if it's purchased new for $45,000, then A equals $45,000. If it decreases by 15%, so R equals 0.15. $45,000. 1 minus 0.15. Well, 1 minus 0.15 is 0.85t. Add this plot to the graph for the truck from example A. Okay, let's go back up here. What was that equation? What was that equation? All right, so that's that equation right there. Let's graph it real quick. Give me a clean sheet here. And what was it? We have 28,000, 28, 1, 2, 3, open parentheses, and then we got 0.905, 0.905, close parentheses, caret, and then we'll just put X, I think is what's there. Yeah. They use T, but we can't use T. I don't even see it. Menu 4, 1, and we don't really care about the negative, so negative 1, 10, and we'll use a scale of 1. And Y min is going to be negative 1. And how much was it worth? It was 28, and this is 45,000. So we'll put we'll put 50,000. We'll put 50,000. 50, 1, 2, 3, and let's see here. We'll do it in 5,000 increments. Oh, there it is. There it is. Good. Now let's plot the other one. And let's see. We'll move that up there like that. And then let's see here. What do we got? 45,000.85. 45,000. So press tab. 45. 1, 2, 3. Open parentheses, 0.85. Close parentheses, caret X. And graph that. It does show up on here. Good. Good. All right. So, yeah. Okay, we did that. The intersection point is, let's see. The intersection point is, and let's find it. It's easy. Menu 6, 4, and that is 7.57. 7.57, and let's go back here, and that's plus 4, so that it's gonna be 13,200. 13,200. You got 1.32, and that's at e to the positive 4. So we're going to move that decimal over. We're going to move it over 4 places. 1, 2, 3, 4, so that just adds 2 zeros. So that makes it 13,200. So after 7.57 years, the value of both vehicles will be about 13,200. Okay. What reference points could you use if you plotted the value function for the sports car on graph paper? Confirm that the graph passes through them using the calculate feature on the graphing calculator. Okay, so we could have, what reference, the sports car, A equals 45,000. Okay, we could have used H is 0 and K is 0. And B is 0.85. So let's see, H A plus K is H A plus, that would be H is 0, so we got 0, and then A plus K, that would have been 45,000 plus 0 is 45,000. Okay, and then we could have used H minus 1, and then A over B plus K, right? And that would have given us -1 and 45,000 over 0.85 plus 0. That would have given us 52,541. Okay, so let's check that. We got this right here, right? Black. That's F of 3. So Control T, there it is. And we had 45,000. We did that. And then -1 was 52,941. 52,541. That says 941. Huh. Off a little bit there. I don't know what. 941. All right. Using the sports car from example B, calculate the average rate of change over the course of the first year and the second year of ownership. What happens to the absolute value of the rate of change from the first interval to the second? What does this mean in this situation? From T sub 0 to T sub 1, we would have 45,000 minus, or 45,000, 0.8 times 0.85 minus 45,000. Okay, and that would have been 1 minus 0. And that's going to give you -6,750 from T sub 2 to T sub 1. That would be 45,000 times 0.85 squared minus 45,000. And that would be 2 minus 1. And that's going to give you approximately -$5,737.50. Okay, so the car depreciates less each year than the year before. So it depreciates each year a little less each year. Your turn. On federal income tax returns, self-employed people can depreciate the value of business equipment. Suppose a computer is valued at 2,765 and depreciates at a rate of 30% per year. Using a graphing calculator, determine the number of years it will take for the computer's value to be $350. Okay, so A is 2,765. B is going to be 1 minus R, which is 0.30, and that's going to give you 0.7. Okay, so here's our equation. F of x equals 2,765, and it's going to be 0.7 to the t. Well, we got to use x with the calculator. All right, so let's graph that. And let's see. What do we got? Graph. We've got 2,765. Open parentheses 0.7, close parentheses caret x, and then enter. Can't see it. Menu 4, 1. We don't care about the negative here, so put -1, and we'll put let's put 5. All right, 1. It's probably going to take more than 5, so maybe make that 10. All right, y scale. Again, we know it's going to bottom out at 0, so we'll put -1 there. And then max, the maximum value was 2,765. So let's put 3,000. And let's see here, maybe a y scale of 500. There we go. Now we can see it. All right, good. So we needed to find the value when $350. The easy way to do that is just press tab and put a line in at 350, and there it is. We got that line. We just need to find that point. Menu 6, 4, and there it is, 5.79. So determine the number of years it will take for the computer's value. So f of 350 would be, what was it? 5.79. 5.79. Good. Which transformation of f of x equals 1/2 to the x power, or f of x equals 1/10 to the x power, change the functions in behavior? Change the function. Well, how do we change the in behavior? Well, instead of approaching 0, we can make it approach -1 or +1 or something like that. So vertical translations change the asymptotes and thus lower the, or change the in behavior. Reflections over the x-axis. In other words, making a negative. Change the in behavior. Let's see. Let's try number 11. Which transformations change the location of the graph's y-intercept? Vertical translations will, horizontal translations will, vertical stretches in compressions, and reflections over the x-axis. So what can change it? The A can, the H can, and the K can. So we've got vertical stretches and compressions. Reflections over the x-axis, over x-axis. So that's the A, horizontal. Translations, left or right, that's the H, and vertical translation, and that's the up and down, or the K. How are reference points and asymptotes helpful when graphing transformations of f of x equals 1/2 to the x power, or f of x equals 1/10 to the x power, or when writing equations for transformed graphs? Well, 0, 1, 0, 1, and that's h, and a plus k. Extremely helpful. -1 and 1 over b, and that's going to be h minus 1, and then a over b plus k. Asymptote y equals k. Those three things make it super easy to graph an equation, or even find the equation from a graph. Give the general form of an exponential decay function based on a known decay rate and describe its parameters. So let's see here. That would be f of x equals a times 1 minus r to the x power. Okay, and I think it used f of t and whatnot. So a, what does a do? A is the starting value. Okay, and then r is the decay rate, and x is the time. Okay, unit of time. How is the graph of f of x equals b to the x power used to help graph the function g of x equals a times b to the x minus h plus k? Well, the b to the x, this one here, that's just, this is the starting point. It's the starting point for the transformation. Great lesson, class. We'll see you tomorrow in school, and have a great evening.